want to start off with just some organization of the material, kind of following the schedule. If you look at the schedule, we're going to follow the schedule as it is written. I was looking at some of the things that we were skipping, and I think it is going to be a good idea to skip. So we left off yesterday with planes. Big topic for today is going to be our dot product. As well as linear combinations. I think we're going to start with linear combinations. I'd rather introduce it first, and then we will come back to this concept of linear combinations quite a bit. Huge concepts in stats, or in linear algebra. So first things first, just a few organizational type things. We are skipping. Let me check the sections. It's 4.8 and 4.9 in the book. So 4.8 is planes. They call it 4.8 planes in Rn, but it's really planes in R3. And 4.9 is the cross product. So do planes via the notes from yesterday. So the way the book does planes, they define it in terms of normal vectors, which is, it's actually a really nice way to do planes, but it doesn't work if you're in 4 dimensions or higher. It only works in planes in R3. So we'll get into the concept of normal vectors and orthogonal vectors today with the dot product. And then you can use that to develop nice equations for planes in R3. Likewise, if you want to find orthogonal vectors and what are called normal vectors, cross product is going to play a pretty big role. Problem is in terms of a bigger concept, bigger picture of linear algebra, is that, well, as I was kind of mentioned, the planes in R3, well, it's only 3 dimensions, so it doesn't really help us describe planes in higher dimensions. Whereas the way we were doing it yesterday, or planes via our notes, we can generalize to 4 or 5 dimensions, however many dimensions. And likewise with the cross product, to really generalize the cross product, you got to get into higher geometry, which is years away from this course. So the cross product only has applications in R3. So it's not terribly important for the bigger picture of linear algebra. I do highly recommend, if you guys have had Calc 3, you've probably actually already seen that, so maybe review that and review that stuff from Calc 3. It is very nice. There's very nice geometric stuff going on. And if you haven't had Calc 3 and you're curious and you have a geometric mind, especially for visual spatial awareness within R3, good topics to look over. But I don't want to spend time on them, so that way we can have time to really see bigger things in linear algebra. Okay, so yesterday we ended off with planes, and the way we are going to be doing planes in Rn, right, we defined as 2D vector spaces. And so I'll try to be really careful with my terminology now, at least for planes. So when I say a plane, I literally mean a 2D vector space, meaning that passes through the origin. if we are talking about a more general geometric plane, a two-dimensional object that sits somewhere in space, I will call those affine planes. So a plane, a two-dimensional vector space through the origin on Rn, we defined as a two-parameter set, namely S times V, or S times U, sorry, plus T times V. Where, so S and T are going to be scalars, and U and V can be arbitrary vectors in whatever dimension we want. The only caveat being that U and V are not scalar multiples of each other. So they are different directions. And we should think about that like it should be fairly intuitive with planes. If I'm on a two-dimensional surface and I'm bound and stuck on that surface, I should have two directions I can walk at some angle potentially. So we'll talk about angles with the dot product. So I'm going to introduce our definition for a linear combination. So given a set of vectors, let's call it U1 up to UK. A linear combination is a vector, we'll say a linear combination specifically of the set of vectors is a sum of scalar multiples of those vectors. Meaning there exists, or let's say for any set of scalars, we'll call them, let's use T1 up to Tk, that are now all scalars, so we're just real numbers. We can define V as just the scalar product. So I'm going to scale each of these U vectors by this scalar T with the corresponding index. And then we're just going to add them all together. And so we say V is a linear combination of the set of U vectors. Or you could say V is a linear combination of the UI, where I is sort of our generic subscript, just denoting our set of U vectors. So examples. Let's say U1 is 0, 1, 2, minus 1. u2 is -1, 0, 0, -3. Let's say u3 is, let's say 0, 1, 1, and 4. Then we could say find v equal to 2u1 minus u2 plus 3u3. So this is our linear combination, scalar multiples of vectors, and then added together. So we've got 2 minus 1 plus 3. So 2u1 minus u2 plus 3u3. And we would just compute that. So v is going to equal 2 times 0, 1, 2, 1 minus 1, 0, 0, 3 minus 3. And then plus 3 times 0, 1, 1, 4. And so you just got to do the arithmetic in each coordinate. So 0 plus 1, give us a 1 in that first coordinate. We'll have 2 minus 0 plus 3, give us a 5 in the second coordinate. 4 minus 0 plus 3 gives us 7 in that coordinate. And then in the last coordinate, we've got 2 plus 3 gives us 5, plus 12 gives us 17. And then let's build a little bit upon the examples we were looking at yesterday. So given a plane, P of ST equal to S times, let's say 301 plus T times -1, -1, and 0. Determine if the vector, let's call it u, equal to, let's see, let's do 4 minus 2 and 2 is on P. So examples like this might show up for this quiz exam on Friday in terms of planes. And so remember, what we want to do is, well, if this is going to be on the plane, that means I should be able to find the scalars S and T that correspond to this vector u. So this gives us a set of equations, 3s minus t equals 4, minus t equals -2, and then s equals 2. So nicely enough, we essentially have our variables solved for. Of course, generally, you might have to do harder work determining the specific scalars that will correspond to this. And remember, we need a consistent solution. So we have our S is 2, our T is 2. So 2 of the equations are satisfied, and then we need to check the third, that 3 times 2 minus 2 equals 4. And that is also true. So since all 3 equations are satisfied, S and T are both going to be 2, and meaning that yes, U is on the plane, and specifically U is going to be let's call our directional vector something. Let's call this one v1 and v2. So this was our first directional vector, our second directional vector, and we know that u is now going to be 2 times v1 plus 2 times v2. In other words, let's take a look at what we've written now in terms of this concept of our definition of a linear combination. What we have shown is that this vector u that is on the plane is a linear combination of the directional vectors. Namely, it's 2v1 plus 2v2. In general, if we look at our definition of a plane now, since S and T are arbitrary, in some sense what we can do is define a plane as the set of all linear combinations of two directional vectors. Does that make sense? So since S and T are arbitrary, this setup right here is necessarily the definition of a linear combination of two vectors. And since we're looking for all sets for any value of S and T, any real number is S and T, it'll give us the collection of all linear combinations of two directional vectors. And again, what you kind of want to think about it is if we are at the origin, that means I can walk however many copies or however many times in the direction of this vector v1, namely we're going to walk s times. And then from wherever I end up after I walk in that direction, we can then walk in the direction of v2, t number of times. And so we're going to generalize this. If not at the end of today, we'll probably start with this tomorrow and start to take a look at now higher dimensional vector spaces. So yesterday we mentioned and drew some pictures on what are the different dimensions. And I kind of mentioned how, two-dimensional vector spaces are planes. And we kind of tried to draw some in R3. If we are in R4, so a four-dimensional vector space, we can still have sub-vector spaces, two-dimensional vector spaces within R4. And those are still going to be planes, but now they're going to have a lot more of them. There's going to be a lot more ways those planes can sit. And so we're going to start to develop a little more formally this algebra of linear combinations that we're going to be able to use to describe our subspaces and our vector spaces, our sub-vector spaces within higher dimensional settings. So before we get too much into that, we want to talk about the dot product and orthogonality. This will sort of close a little bit some of the notions we were talking about in terms of magnitude and size, but it's also going to open up some new things that we need to explore, namely ideas of projections as well as angles. So dot product, angles, and projections. Hopefully this is somewhat familiar. If you've had Calc 3, you've definitely seen the dot product. So our definition, so for u equal to u1 up to un, v equal to v1 up to vn, the dot product Now, dots are kind of hard to draw. In the book, they make sure to draw some pretty big, solid dots. Sometimes it's hard to distinguish between, a dot, a vector dot product, and a scalar dot multiplication. So sometimes we also write it as angle brackets, as a pair of UV. And we also call this the inner product. So usually dot product, of course, comes from the dot. This is often called the inner product, but they are the same thing. And what is it given by? So if you've had Calc 3, the formula is essentially the same. We just need to expand it into n dimensions. Namely, what are we doing? We are taking the product of corresponding positions, corresponding indices, and then adding those all up. Another way of writing it, since this is very much an analog of how we do matrix multiplication, we can write it as U transpose V. In other words, if we were to write U as a row vector, and then do matrix multiplication with V, I did not need to make that big, we would get the same thing. So when we've done matrix multiplication, we look at the row times the column. This is exactly what we mean. I'm taking first position in the row times the first position of the column, second position of the row, second position of the column, multiply those. And then after we do all of those multiplications of those positions, we add them all up. Basic example. Let's do a 41. So U is 1, 1, 2, minus 3. And V is, let's say, 5, minus 1, plus 1, and 0. So U dot V is just 1 times 5 plus 1 times minus 1 plus 2 times 1 plus minus 3 times 0. So we get 5 minus 1 plus 2 plus 0, so 6. Properties of the dot products. The dot product is symmetric. So U dot V is going to be V dot U. It doesn't matter which order we compute our dot product. And again, this is kind of nice. We have started to see, especially with matrix multiplication, that this doesn't always hold. It doesn't always commute. Namely, I can't always change the order of multiplication and still get the same result. So nicely enough with dot products we can. It is positive definite. Namely, that if I take a dot product of a vector with itself, always going to be bigger or equal to 0. And if it's equal to 0, that means the vector itself had to have been the 0 vector. This is a multiplication property, so we want to understand how it works with addition and scalar multiplication. So if we have a linear combination of two vectors, s times u plus t times v, and now we are trying to compute a dot product with a third vector, w, we need a sense of distributive law with all of this. So what we can do is actually compute the dot product. It is a product, so this product is going to distribute over the addition. And then even within the scalar multiplication, we can pull the scalar multiples outside of the dot product. In other words, we can do the dot product first and then the scalar multiplication. And then the last property that a dot product of a vector with itself gives us the square of its length. Okay, so let's prove a couple of fairly important theorems. So these are going to be theorems you yourself won't have to write proofs for. They are going to be properties, though. These theorems are going to give us inequalities that you might have to use either on the homework or possibly exams and quizzes. I do want to walk through the proofs because I do think they are important. And they're not too difficult to understand at this level. So the first theorem is the Cauchy-Schwarz theorem. And the Cauchy-Schwarz theorem says that if I take a dot product of two vectors and then compute the size of that. So do note the notation here, right? A dot product is always going to give us a real number. And we'll talk about what that real number means once we finish these theorems. And so I'm just taking the magnitude, the size of that real number, and that's going to be less than or equal to the magnitude, the product of the magnitudes of the two vectors. And equality only holds if v is a scalar multiple of u. So the proof, we want to look at a function that we define as u plus tv, dot product with itself. So one thing we want to start off with is the 0 case. If the vector v, or if either of the vectors is 0, check the calculation on your own. A dot product of a vector with the 0 vector is just going to give us 0. Again, it's going to be like multiplying a vector by 0. And then, of course, we will have equality. It'll be 0 equals 0. So Cauchy-Schwarz holds when one of the vectors is 0 or when v is 0. So for now, we're going to assume that our vector v is non-zero. So we're defining this function, and note that because the function is a dot product of a vector with itself, so again, we're just taking a linear combination of our two vectors, u plus tv, dot with itself. And by the positive definite property, I know that this has to be bigger or equal to 0. If we expand this out, we're going to get u dot u plus t times v dot u. Those are inside terms. So we did this term, plus t times u dot v, did the outside terms, plus t squared v dot v. And we know that's going to be greater than 0. Simplifying by our properties, this is the norm of u squared. Since the dot product is symmetric, this is going to be plus 2t times u dot v plus t squared times the norm of v squared. So if v is in the direction of u, so v is a scalar multiple of u, namely, so let's use some scratch work to the side. If v is just s times u, then I know that u dot v is going to be s times u dot u, which is s times the norm squared of u, which we could write as norm of u times the norm of s times u. In other words, we get equality of norm of u times norm of v. So that case, fairly straightforward. If v is a scalar multiple of u, Cauchy-Schwarz inequality we proved directly by computing, and we saw that equality holds. So now with our procedure, we want to assume not only is v non-zero, but that v is not a scalar multiple of u. And so if v is not a scalar multiple of u, then that means that this u plus tv cannot be 0. Since v is going to be pointing in a different direction than u, I cannot take a linear combination of u and v and have these vectors be 0. So if I'm taking a dot product of a vector with itself, and that vector is non-zero, we are going to have strict inequality. Namely, the dot product is going to be specifically greater than 0. And so if you look at what we have, we have a quadratic function that is strictly bigger than 0. And so from there, we can deduce, so quadratic function bigger than 0 implies from pre-calc, if not calc 1, that there are no zeros. So it doesn't cross the t-axis. In other words, the discriminant is 0. So what is our discriminant? If t is our variable, our discriminant is going to be b squared minus 4ac. In other words, 2 times u dot v squared minus 4 times a. So that coefficient is norm v squared, and c is norm u squared. And so that discriminant, the discriminant is strictly less than 0. Meaning that if we were to try to solve this quadratic equation, we would have imaginary roots. So we can divide everything by 2. And what do we get? U dot v squared. If we wanted to do it properly, let's write it as u dot v minus, oh no, sorry. So that 2 squared would be a 4. So the 4s would cancel, and we just have u dot v minus norm v squared, norm u squared, which we can write as this. So we have a difference of squares. Sorry, I'm off the page there. And so what do we get from this? From this, essentially, we deduce that our u dot v has to be less than our norm of v times norm of w. And so that is our Cauchy-Schwarz inequality.
Sorry, can you just put the equation at the very bottom of the last page at the top? Thank you.
Okay, so our second theorem is going to be the triangle inequality. Triangle inequality says that if I add two vectors, then it's going to be the less than or equal to the sum of the lengths of the two individual vectors. So we drew a picture for this the other day and showed why so if we have vectors u and v and then u plus v, that the sum of two individual lengths of a triangle should always be bigger than the third. So we can prove this using the Cauchy-Schwarz inequality. Primarily, if we take a look at the norm of u plus v squared, that's going to give us the dot product of the vectors u plus v. So sorry, my pages are getting angled here. And by our properties of a dot product, this is going to be u dot u. So we're just going to distribute plus 2 times u dot v. So that's going to be v dot u plus u dot v plus v dot v. And by our Cauchy-Schwarz inequality, we know that this is going to be less than or equal to norm of u squared plus 2 times norm of u times norm of v plus v dot v, or norm of v squared. And now this term on the right is a perfect square of the norm of u plus the norm of v all squared. And so when we take a square root of both sides, since both of these terms are going to be positive, we arrive at our conclusion. So these properties of the dot product, these are fairly important geometric properties of vectors, both the Cauchy-Schwarz and the triangle inequality. So the triangle inequality might come up, as well as the Cauchy-Schwarz. We could do examples. Let's see. I don't really want to compute any examples of those just yet because I'd like to move on and do some examples with the geometry and projections. So maybe we'll see how these might come up in proofs. So you guys aren't going to be writing too many proofs for this course. So these might come up once or twice, but it's not going to be terribly rigorous at this level. So let's talk about the geometry of the dot product. So let's start off with a well-known formula that the magnitude of the dot product, so if I take u dot v, oh, sorry, actually not the magnitude. U dot v itself is a scalar. It's a real number. We can write this as norm of u times the norm of v. So the length of u times the length of v times the cosine of theta, where theta is the angle included between u and v in the plane they define. So if we take our vectors u and v as directional vectors in a plane, in that plane we can draw an angle between u and v, and that gives us the angle theta. So, basic examples. Find the angle between u equal to minus 102 and v equal to 5 minus 2, 3. We now have a tool to do that. So our first step is to compute the dot product. So u dot v is minus 5 plus 0 plus 6. So it's just going to be 1. We need to compute the norm of each vector. And then we just plug them into our equation. So we're going to have 1 is equal to norm of u times norm of v times cosine of theta and so we get cosine of theta is 1 divided by square root of 5 times square root of 38 Let's see. Do we want to write that as square root of 5 times 30 is 150? So it's going to be 190. And unfortunately, if the numbers aren't nice enough, about the nicest thing we can get without a calculator is going to be inverse cosine of 1 over square root of 190, which if we wanted to use a computational device, let's check it real quick. Looks like we're getting about 1.5, 1.498. So this is about 1.5 radians. So in degrees, we're getting about 85.8 degrees. And so, of course, the nice thing to point out is that this works in higher dimensions, right? If I just have two vectors in higher dimensions, one being able to describe the plane by those two vectors takes a little bit of work. And if we actually had to measure an angle by some other geometric means, it could get rather complicated. Dot product is a nice way to give us a nice formula for that. Of course, computing the arc cosine of whatever those values end up, not easily doable by hand, but like a test or quiz, something like this, be a perfectly fine answer. It is what it is. Arc cosine of 1 over the square root of 190. So moreover, the other thing that the dot product can tell us is the notion of orthogonality and perpendicular, right? So recall that cosine of pi over 2 is 0. So our definition, we want to call two vectors perpendicular if the angle between them is 90 degrees. It's pi over 2 radians. And this is exactly what we want to do. But again, angles and vectors in higher dimensions, depending on your orientation, you could look at it weird. And if you're not in the correct plane of those vectors, the angle might look different. So now we have a more rigorous mathematical tool to define that. So two vectors. U and V and Rn are orthogonal. So this is the other word we like to use in linear algebra. Orthogonal or perpendicular. If their dot product is 0. So for example, if we have two vectors, u and v, let's say 2, 1, minus 1, and v equal to 1, 3, 5, we can ask something like, check to see if they are orthogonal. So when I take a dot product, we get 2 plus 3 minus 5 equals 0. So u and v are orthogonal. Some other examples. So this is a common example to do in 2 dimensions. Find a vector, and maybe we'll do a second part trying to find all vectors perpendicular or orthogonal to a given vector. So what do we want if v is v1, v2, and u dot v is 0, then this implies that 2v1 minus 9v2 is equal to 0. So we have two unknowns we are trying to solve for, v1 and v2, and we have one constraint equation. Meaning there's not just one vector that's orthogonal to u. There's infinitely many vectors that are going to be orthogonal to u. So if we want to find one, if we just want to find an easy one, the easiest trick is, well, my components of my components of u are 2 and negative 9. And if we want to just sort of undo their operations, if I flip them, so do 2 times 9 minus 9 times 2, in other words, I flipped those coordinates and then made one of them negative. I know that will work in giving us a 0 just by our properties of multiplication. So what we chose there, v1 equals 9, v2 equals 2. So this will give us one choice and find one orthogonal vector. So notice now that if we started with our vector 2, negative 9, all we had to do was flip the coordinates and then make one of them a negative of what it was. And hopefully learned from pre-calc or calculus, 2 lines are perpendicular if and only if the slopes are negative reciprocals. In other words, our m1 is negative 1 over m2. So this should be raising some alarms here of what's going on. So generally, we've talked about lines. What is a line? if we had a line through the origin that followed in the direction of u, it would look like this. All right, this is our u vector here. And this is our x coordinate. This is our y coordinate. And really what you want to think of it as the change in y, x, and the change in y. So vectors are a generalization of slope. This is why we actually need vectors for 3 dimensions, because I have x's, y's, and z's. So we need a mathematical tool to be able to model the relative rates of change in all coordinates. And so we can kind of think that this is my line. For every tick of time that goes by, when I start at t equals 0, we're at the origin. After 1 second, I move along the x direction 2, and then in the y direction, we move -9. The next second that ticks, we'll move 2 more in the x direction, -9 in the y direction. So our slope would correspond to -9/2. That's our change in y over our change in x, going from our parametric equation for a line to something like a standard y equals mx plus b. So perpendicular should be something like 2/9, which is then going to correspond to what vector? Again, this is our change in y, our change in x. So the vector corresponding to a slope of 2/9 is going to be 9, change in x, 2, change in y. So we might write something like L, oops, that's a terrible L, L perp, the line through the origin perpendicular to this line, will have our directional vector 9, 2, and then scaled for time. And we now have this tool, this orthogonality of dot products. We can check now and verify that those two are, in fact, orthogonal. They do meet at 90 degrees. And so this trick, it works in 2 dimensions. Of course, we didn't find all vectors that are orthogonal to that. If we wanted to find all vectors that are orthogonal, we would take scalar multiples of this guy. Once we have one line or one vector in a 2-dimensional plane, as soon as I find one vector that is orthogonal to it, then every other vector that is orthogonal is going to be along that line. So it's going to be a scalar multiple of that vector. And we can show that if we wanted to by the equations we have. So the defining equation for our u dot v was we needed 2v1 minus 9v2 to equal 0. In other words, if we wanted to find our v2, it's going to be, we would subtract our 2 over 2v1 and then divide by 9. And so what's this going to imply? That our vector v is going to have the form v1 and then 2/9 v1. In other words, it's going to be all scalar multiples of this vector with a free choice of whatever scaling factor we wanted. In other words, since v1 can be any scaling factor, we can sort of rescale our scalars and write v1 is equal to something like 9 times t. And that would give us 9, 2, times d. So all scalar multiples of that orthogonal vector we found give us the entire set of vectors orthogonal to u. And now if we try to do this trick in 3 dimensions, it gets a little more tricky because now we're not going to be able to find all of the vectors, at least easily, that are orthogonal. Sorry, did everyone get those notes there? So if we try to find find a vector orthogonal to u is equal to 3 minus 8, 1. We can kind of use the same trick, but if we wanted to find all of them, we're going to have to be a little more careful. It's going to be a little more broad. And so now with this notion of lines and rates of change, you should kind of think of, if I have a vector pointing in this direction, this is now geometrically, it's like an analog to slope, or is what our directional vectors are. This is like a change in x, change in y, and change in z for every unit time that ticks by. And the problem is that there's not necessarily like a unique way to just, flip the coordinates. We can try a similar trick. Namely, if we just choose v equal to, we can simply flip the first 2 coordinates, or pick any of the 2 pairs of coordinates, flip them around and change one of the minus signs. So let's make the 8 positive, and we'll keep the 3 with the same sign. Flip their positions, and then what are we going to do? Let's just throw in a 0. Zeros are nice for dot products because we can just eliminate essentially that component of the calculation. So now when we compute u dot v, we'll have 3 times 8 minus 8 times 3 plus 0. Alternatively, we could have done something like choose w equal to, let's flip the bottom 2. So we will have a 1 here and an 8, pick the other coordinate at 0. So now when we do u dot w, what do we get? We'll get 0 minus 8 plus 8 equals 0. So again, found an orthogonal vector. In general, if we wanted to create a generic variable, so let's call it y, we're going to have 2 free parameters. And so let's see what's going on with that. U dot y is just going to be 3y1 minus 8y2, and then plus y3 equals 0. And if we want those perpendicular, typically we usually solve for the last coordinate in terms of the other 2. And so our y is going to be any vector of the form y1, y2, and minus 3y1 plus 8y2. Meaning that we have 2 free parameters. I can choose y1 and y2 however we want. We can pick whatever values we want for y1 and y2. And then the third value will essentially be dictated by this orthogonality condition. And this is what we should expect, right? In 3 dimensions, if I have a vector, we should have an entire 2-dimensional object, namely a plane, is going to be orthogonal to this given vector. So we have a choice in 2 parameters as we rotate around that plane. So there's an entire plane, a two-parameter solution of values that are going to be orthogonal to a given vector that can rotate around that plane. And we can find them by a given parameterization. So check that if you're interested in the geometry and correlate it back to these orthogonal planes if you want to read section 4.8 or 4.9 in the book, and try to find normal vectors and normal planes to given vectors. Okay, so lastly, what we want to talk about in terms of the dot product are projections. So let's say we have two vectors, u and v, and we have some angle between them, theta. And we know that the dot product, u dot v, is given by the norm of u, norm of v, times the cosine of theta. Well, if we orient it in a certain way, so that I draw a perpendicular vector from u, draw a right angle here. Then this length, actually let's draw it here as well. Then this length well, how would we compute it? You should be able to check that it is going to be the length of v times cosine theta. So this just follows from our basic trig. Namely, cosine of theta is going to be the length of this base here times, or divided by, the hypotenuse, or the length of the hypotenuse, which is the length of v. So in some sense, what you can interpret a dot product as we've got this u vector times this norm v cosine theta. Is norm v times cosine theta is what we want to call the projection onto u of v. We're saying if we use u as a point of reference, as our line of reference, then if I were to project v onto u, and when we project, we mean orthogonally project, we want the component of v, in some sense, that is pointing in the direction of u. Then we would simply have to take v cosine of theta, and then of course we might want to tag along a notion of the direction. Does that make sense? Geometry, pictorially, what we're doing here? And I guess to be clear, when I say projection of v onto u, we should simply say the size. So that length is going to be norm of v cosine of v. So another way of interpreting u dot v is a scaled projection of V onto U, or vice versa. If we wanted to orient our frame with V as like a base value, we could just as well go perpendicular to V and look at what component of U projects onto the direction of V. And then that'll give us U, norm of U, cosine theta, would be this red length. And then we would scale that length by the norm of V. And that would give us our dot product. And it turns out that those scalar multiples of those corresponding lengths are going to be the same. So I'll leave it to you guys if you want to play around with the geometry and take a look at that. So let's formalize some of these processes now and see what we can, how we can use this concept of projections and this dot product calculation to break vectors down into what we might call component vectors along the direction of other given vectors. So to find the component of V along U, we need one, the dot product, so U dot V, and two, we need to unscale this. i.e. make U a unit vector. Right, so we have this V, norm of V times cosine of theta gives us this length, this green length that we want to compute, or we want to be able to find. What is this component of V in the direction of U? However, if we take this green length and then multiply it by the magnitude of U, it's going to stretch that length. So really what we want to do to find a projection is to simply rescale our vector that we want to represent this base direction. If we want to project V onto U, we would want to make U a unit vector. So in other words, if we take V dot U over its norm, so if I take a vector and divide by its length, that gives us a unit vector in the same direction as the given vector. This guy gives us our green length. So it gives us the size of that length. However, if we want to keep that direction, well, what's the direction we're going in? We're going in the direction of U. So we would just multiply it then.
Nope. Termina en unos 10 minutos.
No soy el maestro.
Pues tengo mis headphones.
So that'll give us the green length if we want to find the vector component of V in the direction of U. We would then multiply this scalar by the unit vector in the direction of U. In other words, if we want to project onto U the vector v, we are going to compute the dot product of v dot u. Because this 1 over norm u is a scalar, we can pull it outside of the dot product. And then we are going to multiply by the unit vector in the direction of u. So all in all, we get v dot u over the norm of u squared, and then multiply that times the vector u. Any questions on that? Okay, so this brings up a theorem. So given two vectors, u and v, and Rn, there is a unique way to write v. The notation's a little weird. It's going to be hard to write, but we write it as v parallel. So think of that as just two parallel lines, not an 11, plus v perp, where v parallel is in the direction of u, i.e., so we call it the component of v in the direction of u. And the perpendicular is the perpendicular component or orthogonal component of v in the direction of u. The proof is fairly straightforward. It'll be better to do an example. Let's write down the proof and then show an example. So we will just simply take v perpendicular is the projection onto u of v, and then the perpendicular component, sorry, did I say perp there? V parallel is the projection. And then to find the perpendicular component, you simply take v and subtract off the parallel component. do an example. Let's suppose we have our u is 2, 3 minus 4. And our v is 1 minus 2, 1. And what do we want? We're going to find the parallel components and the perpendicular components of v onto u. So our projection of v onto u is found by taking the dot product, dividing by the norm of u squared in the direction of u. So I guess I should write it like that. So that's not a dot product, that's a scalar product there. So let's pick out our pieces. As with a lot of these problems, the math behind it isn't hard, it's just lengthy. So there's a lot of computations to do. So our u dot v is going to give us 2 minus 6 minus 4. And so that's going to give us negative 8. Our norm of u squared is just going to be 2 squared plus 9 plus 16. Just go ahead and square everything. So 29. And so our v parallel is going to be minus 8 over 29 times v, or excuse me, times u. You can leave it like that. So with these types of calculations, I'm fine with you guys leaving like a scalar multiple times a vector, especially if multiplying those out, it's not going to make things look nicer, right? It's easier to write it as this scalar multiple. Multiplying things out, not too difficult. We're just going to have to throw in that denominator in each component. And then the third one, 32 over 29. And it kind of just makes a lot more to write out. So running out of space on this page, let's try to write it on our next page. So we had our the parallel is minus 8 over 29 times 2, 3, 4, negative 4. And so that's equal to minus 16 over 29, minus 24 over 29, and 32 over 29. And then our v was 1 minus 2, 1. So our perpendicular is just going to be v minus the parallel component. So we just take the original vector, subtract off the parallel component to get the orthogonal component. So note this is a specific orthogonality. In our previous examples, we kind of showed in 3 dimensions and especially higher, there's not unique orthogonal vectors to a given vector. There's going to be a parameter of solutions. However, if we only have 2 vectors that we care about, and I subtract off the parallel component, we are looking for a very specific perpendicular component. And so it's going to be an exercise for us to make sure we check that this perpendicular component is in fact perpendicular to u. So our v was 1 minus 2, 1. And we have to subtract off this guy. So let's go ahead and distribute that minus sign. Let's just make it plus. This will be 16 over 29, 24 over 29, and then minus 32 over 29. Could have had better numbers, but we got to work with what we got. So 1, 16, and 29 is going to give us, what, 45? It might even be helpful to just pull out the 1 over 29 if you want to. So minus 2, that's going to give us a negative 58. Plus 24 is going to give us 34 negative. And then 1's going to give us 29 minus 32 gives us negative 3 out of 29. Let's write it as 1 over 29 times 45, negative 34, and negative 3. Everyone still with me? So sorry, we're a little bit over. Just check real quick. Let's see if we can do that calculation. We should have that u and v perp are in fact perpendicular. So their dot product should be 0. Our u was 2, 3, 4, negative 4. And our v perpendicular we now found as 1 over 29. Which nicely enough, we can bring outside of the dot product. 45 minus 34 and minus 3. Will that work? So we've got 1 over 29 times 90 minus 94. Is that what that is? So 3 times 34, sorry, minus 1, 12. Or 102, yeah. Minus 102 plus 12. And what's that give us? So our math worked out all of our arithmetic. And we see that this perpendicular component is in fact perpendicular to this base vector, this u. Any questions?